In this video, we're going to introduce and define the idea of a group. So a group is a kind of algebraic structure in which we have one operation that satisfies certain properties. Here's the definition. So definition, a group is a set G together with a binary operation star on G having the following properties. So I'm going to define this in a way that's a little bit different from the definition given in Galilean. The definition given in Galilean is perfectly fine and sufficient. I added property just to emphasize a specific aspect of having a binary operation, but actually the property I'm about to state is really covered by star being a binary operation. So the first property is, for all A and B in the set G, the result of the operation A star B is an element of G. And this is called closure. In other words, G is closed under the operation star. Now you recall that what I just stated here, that G is closed under the operation star, that's actually part of the definition of having a binary operation on G. That is, if this isn't true, if property 1 isn't true, then I can't really say that I have a binary operation. So technically stating this property is unnecessary, but it's kind of a nice thing to keep in mind as we're checking whether something is a group or not. Okay, property 2. For all A, B, and C elements of G, A star B, the result of that star C, that's an element because this gives an element of G here, and this is an element of G here, so I can operate with these two together. And that's going to be equal to what I get if I start with A and then operate that together with B star C. So this is saying that star is an associative operation. Okay, so that's property 2. In order to call something a group, the operation on it has to be associative. All right, property 3. There exists some element E belonging to G such that for all A belonging to G, E star A and A star E are both equal to A. And if that's the case, then we say that E is an identity element. So E is an identity element for G. Okay. By the way, one habit that I have from my own practice of group theory is sometimes instead of calling this element E, I'll call it something else. Like I'll call it 1. I'll use the numeral 1 to represent that element. So look for me to do that sometimes. Sometimes I call it E, sometimes I call it 1. And there can be other symbols as well, depending on what specific group we're working in. All right, and finally, for every element A belonging to G, there exists an element A inverse also belonging to G such that A star A inverse and A inverse star A are both equal to E. And if that's the case, then we say that A inverse is an inverse for A. So here what we're saying is that every element of G has to have an inverse. All right. By the way, one little quick note here. One specific element that has to belong to any group is this element E, this identity element. Does that have an inverse? Think about that for a minute. Can you think of what might be the inverse of E? So we want to find some group element such that E star that element equals E. That would make this thing the inverse of E. And what you may have figured out by now is that the element E works perfectly well. So E is its own inverse. And that's always the case. In any group, the identity is its own inverse. And sometimes there may be other elements that are their own inverses, and sometimes that might not happen. Okay, so these are the 4 properties that we have to have in order to call something a set together with an operation a group. We have to have closure, we have to have associativity, we must have an identity element, and we have to have an inverse element for each element of the group. There is an additional property that a group might have, but it's optional. So I'll call this property 5. But I'm going to block that off just to make sure it's very clear that we only need properties 1 through 4 for a group. So if we have this additional property that for all A and B and G, that A star B is equal to B star A, then we say that the operation star is commutative. And we also say that G is an abelian group, assuming that all the other properties hold. So if we have a group and its operation is commutative, then we call that an abelian group. Sometimes people capitalize the word abelian because it's named after the mathematician Abel. I usually just write it in lowercase. So now let's look at a couple of examples. So I'm going to zoom this out so we have it available, but it's not totally in our way. Okay, so we're going to use that as a checklist to determine whether something is a group. All right, so let's start with the group Z mod 5 that we talked about in a previous video, the one on binary operations, and its addition operation, addition in mod 5. Okay, sometimes when we write a group like this, we put it in an ordered pair with the set first and then the name of the operation after that. That's a pretty standard way of writing down the name of a group. All right, so recall from a previous video that we said Z mod 5 has 5 elements. We can think of them as these points on the face of a clock. Well, a clock with 5 marks, which is kind of a strange clock. 0, 1, 2, 3, and 4. And we had a way of defining addition along the clock. It was, if I want to add, for example, 3 plus 4, then I start at 3, and then I count up 4 times. 1, 2, 3, 4. And wherever I end up, that's the result of my addition. Okay, I claim that this is a group. But to do that, to make sure that that's true, we actually need to check some things. First of all, we need to check closure. That is, we need to check whether any 2 elements of Z mod 5 can be added to give another element of Z mod 5. And that is something that's true. We verified that in the previous video by working out the entire addition table. So that's known because we have an addition table, and any 2 numbers in this system can be added. Okay, associativity. I'm going to claim for now that that is a property that this addition operation has. I have not verified it yet. So we actually have this, but I'm not going to prove it in this video. So to prove that an operation is associative just by checking, even when we have a group as small as 5 elements like this one, can be really tedious because we have to check all of the facts involving, well, we have 3 variables to choose values for, A, B, and C, and for each variable there's 5 possible values, so we'd have to work out a lot of facts. The reason that we know Z mod 5 addition is associative is because it is sort of filtered down from addition of integers, which we know to be associative. So I'm not going to go into any more detail on that right now. I'm going to focus on verifying the other properties. All right, the identity property. I believe that we do have an identity, because one thing you might remember in the last video is that we checked that if I take any number in Z mod 5 and add 0, I get that same number. And if I do the addition the other way, I still get the same number. So 0 is an identity element. You know, one thing that just occurred to me to say is that in the definition we call the operation star, but over here you'll see that we are using the plus symbol. We can call the operation whatever we like. For a lot of groups we use the plus symbol rather than multiplication. All right, finally, inverses. Well, can we verify that each number has an inverse? We already talked about how the identity is always its own inverse, because 0 plus 0 equals the identity 0. What about 1? Can we think of anything which adds to 1 to give 0 in Z mod 5? Well, if I start at 1 and just start counting 2, 3, 4, and then end at 0, well, I've counted 4 times. So I think that if I add 1 plus 4, I will get 0. So that means that 1 and 4 are each other's inverses, because I can also check that 4 plus 1 is equal to 0. And once I know that both of those things are true, I actually know two things. I know that 4 is the inverse for 1, and also I know that 1 is the inverse for 4. So 1 and 4 are each other's inverses. And finally, what about 2? Does 2 have an inverse? Well, I know that if I start at 2, I can march around until I get back to 0. 1, 2, 3. So 2 plus 3 is going to be 0. And I can also verify that 3 plus 2 is 0. So that means that 2 and 3 are each other's inverses. Okay, so 0 is its own inverse. Let me put one little arrow there. There we go. 0 is its own inverse. And then 1 and 4 are each other's inverses, and then 2 and 3 are each other's inverses. Everything has an inverse. And also, one thing that we know from our addition table from the previous video is this operation is commutative. So addition is commutative, which means that not only do we have a group, we in fact have an abelian group. Z mod 5 is an abelian group under addition. So that's one example. We'll talk about another one in the next video.